Although we don't see stars age because that process takes longer than a human lifetime, we do see billions of stars, so we have lots of examples. And we also deduce what happens during a star's lifetime through stellar models, which make use of equations of physics, specifically those of stellar structure. The interstellar medium is about 70% hydrogen and the rest mostly helium. Higher density regions form clouds where star formation takes place. These are often called molecular clouds because the hydrogen tends to be in its diatomic form, H2. At the beginning of star formation, an interstellar gas cloud collapses due to gravity. Any rotation in the contracting gas clump makes it flatten into a disk. Conservation of angular momentum causes the disk to spin faster when more and more mass migrates to the center. The center of the disk forms a small dense core called a protostar. Energy released by gravitational contraction is often greater than the energy produced by deuterium fusion until the deuterium is used up. Radiation from this energy is in the infrared part of the spectrum. Gravitational contraction continues in the protostar until pressure is sufficient to halt it, and that only happens when fusion begins in the core. Sometimes at this phase, bipolar jets, due to a star's magnetic field, will help clean up its vicinity. When a star begins fusing hydrogen into helium in its core, the main sequence has begun. This will last until about 90% of the hydrogen in its core is used up. We can estimate how long a star will be on the main sequence by taking its mass in solar masses and dividing by its luminosity in solar luminosities, and then multiplying by 10 billion. Then we get a result in years. At the end of the main sequence, the core will contract and heat up, increasing the rate of fusion, which causes the photosphere to expand and cool, turning the star into a red giant. During this phase, hydrogen fusion occurs in the shell, no longer in the core. Eventually, the core will contract enough that the temperature is high enough for helium fusion to begin. A star whose total mass is under 2 solar masses undergoes what is called a helium flash, a rapid release of energy, and then becomes a yellow giant. When it has consumed most of the helium in its core, the star changes back into a red giant, but even larger and more luminous than before. The increase in radiation from its core expels the outer layers of gas, and they eventually disperse into space, exposing the core. The dispersed gas is called a planetary nebula, but it does not have much to do with planets. That's just the name that has stuck. And the core of the star remains as a white dwarf. A white dwarf is a stellar core remnant composed mostly of electron-degenerate matter. They are roughly the mass of the sun, but the size of the Earth, so they are very dense. They shine by residual heat from their interior. With no fusion occurring, they gradually cool. Contrary to what you might expect, if mass is added to a white dwarf, its radius shrinks. It is becoming even denser. If its total mass ever reaches about 1.4 solar masses, it crosses the Chandrasekhar limit and explodes as a supernova. Roughly 8 solar masses is the amount of mass required for a star to be considered high mass. Their main sequence is hotter, bluer, more luminous, and lasts shorter. That's because it goes through its fuel faster. At the end of the main sequence, it becomes a pulsating yellow giant and then a red supergiant. With its higher temperature, it fuses heavier elements in its core, helium to carbon, carbon to oxygen, and ultimately silicon into iron. Since iron does not release energy when it fuses, iron fusion would not support a star against gravitational contraction. Protons and electrons merge, so to speak, into neutrons, thus decreasing the pressure that is supporting the core. So then the core collapses. The outer layers strike the neutron core and then rebound. The star explodes as a supernova. In a supernova, heavier and lighter elements are mixed as they're flung outward, sometimes at velocities greater than 10,000 kilometers per second, which corresponds to 3.3% the speed of light. A tremendous amount of energy is released in a supernova. In the background image on this slide, a supernova appears in the bottom left of this galaxy. You can see that its light briefly outshines the light of the rest of the galaxy. If the total mass of the original star was between about 8 and 20 solar masses, then the remnant core after the supernova is a neutron star. A neutron star has the mass of the sun, or maybe 2 or 3 suns, but is the size of a city. It is much denser than anything we experience. Some neutron stars are pulsars, emitting radio signals at regular intervals. The rate of pulsation, which was later determined to be due to its spin, is inversely proportional to the square root of its density. The reason they can spin so fast is due to conservation of angular momentum. Since the radius has decreased by a lot, the angular velocity can increase by a lot. Neutron stars also have extremely strong magnetic fields, which generate beams of charged particles from the star's magnetic poles. The neutron stars with the most extreme magnetic fields are called magnetars. Over time, neutron stars eventually slow down in their rotation, with the exception of occasional glitches when its surface shape is adjusting itself and the rotation rate can briefly increase. When two neutron stars are close enough to orbit each other, they can generate gravitational waves, which spiral outward, distorting space and time. In 2017, the Laser Interferometer Gravitational Wave Observatory, also known as LIGO, detected the gravitational waves of two neutron stars merging together. And 2 seconds later, the Gamma Ray Observatory, which is in orbit around the Earth, detected a burst of radiation. With other telescopes, astronomers were able to find the supernova that was rapidly fading. We now think that events like this are responsible for most of the elements heavier than ruthenium, atomic number 44 on the periodic table. If the total mass of a star during its main sequence is greater than 20 solar masses, then it will likely become a black hole when it collapses. Black holes are black because the escape velocity is greater than the speed of light, so not even light can escape from them. You might remember the equation for escape velocity, which we saw when we talked about rockets. Escape velocity, v escape, equals the square root of 2g, gravitational constant, times m, the mass of that central body, over r, its radius. So if we set this escape velocity equal to the speed of light, we can find what this radius is. Square both sides. And we solve for r. This radius is known as the Schwarzschild radius. From within this radius, no light can escape, and it is set simply by the mass of the black hole. Because nothing can travel out from a black hole, we call that boundary the event horizon. We cannot see anything that happens inside. Black holes attract other masses just due to gravity. They do not suck like a vacuum. But near them, they do have strong tidal forces. So if a mass is approaching the black hole, The part of it that is closer to the black hole will be drawn gravitationally towards the black hole with greater force than the part that is further away. So as a result, the mass is stretched, and we often say it is spaghettified. Black holes can then grow by eating more mass. We find black holes at the centers of galaxies that have masses greater than 1 billion times the mass of the sun. It turns out, however, that black holes are not completely black. Their temperature is slightly above absolute zero, and by Hawking radiation, they emit energy so they can eventually evaporate after approximately 10 to the 67 years, if the universe even lasts that long. LIGO has detected gravitational waves from several black hole mergers, and the first direct image of a black hole was published in 2019 and is the background of this slide. To capture this, they had to use telescopes set up across the whole Earth as an interferometer. We can only see this black hole, so to speak, because we caught it in the act of eating other mass. It's brighter on one side because it's spinning. Our sun is not massive enough to become a black hole or a neutron star. Instead, it will become a red giant and will boil the Earth's oceans as it grows. Eventually, it will release its outer layers, become a planetary nebula with a white dwarf at the center.